Well, hello everyone. This is Han Li from TI Education Group. Today I'm going to present our paper, Learning Fine-Grained Cross-Modality Excitement for Speech Emotion Recognition, aka SER. So before we start, let me first give you a brief introduction to the SER problem. So the goal of SER is actually ask us to recognize the emotion contained in the speaker's utterance automatically. And the emotions will usually including like the neutral, happy, sad, surprise, or something like this. And since the emotion expressions of the human beings are always complicated, so the multimodal learning as an efficient way to integrate the information from different modalities has widely been accepted by the current researchers to solve the SER problems. So in this graph, it's actually it's a representation for the prevalent multimodal learning algorithms for solving the SER problem. So first, you can see we have the inputs from different modalities, like the transcription of the speech and audio signals of the utterance. And then these algorithms will always design the separate encoders for each modality's inputs. And then based on that, and based on these encoders, we can get an efficient sentence level embeddings for each modality. And after we get that, we will feed these two embeddings into a fusion module, which actually trying to catch the interactions between the features from different modalities and generate more representative embeddings for the whole sentence. And when we get the final multimodal fused representation, we will feed into a classifier to tell us which is actually the emotion should the spoken sentence should be, and this kind of pipeline is actually quite simple and straightforward, but actually it has a problem. So since the fusion of the embeddings actually happened after the information extracted for the modalities in the sentence level, so some fine-grained interactions between the different modalities is dismissed. So based on this fact, we actually in our research, we designed fine-grained fusion algorithms, which actually move the fusion process and directly after the model accept the inputs from different modalities. So if you look the paired samples in the left side, we actually first use some very simple tokenizers to tokenize the speech sentence into different tokens. Then, based on these tokens, we use some pre-trained aligners to help us to find the corresponding audio signal for each token. And then based on this fact, we can extract the embeddings from different modalities in a token level. And then we try to design some efficient multimodal fusion algorithms for these token embeddings. And then when we successfully fuse the embeddings for each of the tokens, then we apply the some sequence modeling algorithms like the RN model to extract the sequence information of the whole sentence. And finally, we will feed the sentence level fused embedding into the classifier like the most of the current works. So here's the problem about how can we perform such fusion. The first and most simple token level fusion is actually to concatenate the information from different modality directory. And actually, this algorithm have already been tried by prior researchers, but they find such algorithms or such strategies don't work well. So we get some inspirations from the computer vision field, which they will design some excitement block to enhance the representation of the whole graph based on some strategies. So in our case, we think we can think it very similar. So for a given word or given token, we can apply a linear projection layer to map the token embeddings into another space, hidden space. And then we apply a sigma function to make sure that each of the value in the dimensions are converged, are compressed between 0 and 1. And after we applying that, we can actually regard it the generated vector as a gate function. And it's actually we apply a Hartman production with the embeddings from another modality. So when we do such process, we can regard it as we design a filter based on the given token. And then since we have its corresponding acoustic embedding, then we apply this filter for its corresponding acoustic embedding. And actually this process is telling the model to get the most relevant acoustic embedding for such token. And we can also do the same things in the other direction, which we get the acoustic embedding first, then we generate a gated filter with the linear projection and the sigmoid function, and use that generated acoustic-based filter to the semantic embedding. And then after we get these two embeddings, we will fuse them together. And then finally, the token level fused embedding are generated. Well, after we introduce the cross-modality excitement block, let's have a look about the whole model's framework. So from the bottom to the top, these modules are encoders, alignment, alignment process, cross-modality excitement, and sequence modeling process. So for the acoustic and semantic encoders, we actually used a different strategy. So since usually the raw feature for the signals are actually extracted in the frame level, so we actually will simply apply some one-dimensional 1D convolutional neural networks to extract the local contextual information. And then for the semantic information, we usually use very simple pre-train the word-to-vec embedding models and try to map the split tokens into the word embedding representations. And since just we mentioned acoustic information are usually extracted in frame frame-wise. So before we apply our cross-modality excitement, we need to align them together. So here we use some current available alignment algorithm like the force alignment. So we will ask the model to tell us so in which of the frames are actually corresponding to some specific tokens. And when we get such information, then we can aggregate these frame level information into the token level information. And the aggregation algorithm here we used is mainly based on the min-max pooling algorithm, which has been proven to be very effective in preserving the acoustic features for the following process. And then when we get the both the token level semantic and acoustic embeddings, we will feed them into the cross-modality excitement module that we just introduced. And then we will get the fused token level fused embeddings. So so then we will also add a final bidirectional long short-term memory network to help us to extract the sequence information between the tokens. After that, we will finally apply a max pooling layer to convert the token level embeddings into a sentence level embeddings and for the final classification task. Well, yeah, so here let's go to the experiment details about our research. So to prove the effectiveness of our algorithm, we actually choose two public available data set. The first one is the IEM-CAP. It consists of 5 sessions of dynamic conversations between different pairs of actors. And actually they have like 10,000 answers are collected. And then we also incorporate the RevDis dataset, which contains 9 hours of speeches and 1,400 more utterances. And each of the label of the utterances is validated by multiple raters. But to be noticed, unlike the RevDis, unlike the IEM-CAP, the speech content of each utterance is actually very similar with each other. And the only difference is that the actors is actually trying to express the different emotions through their different tones. So which means the whole process actually could be more difficult than the IEM-CAP. And for these settings, so to have a comparison with